In this lecture, I will talk about symmetric cryptography and how we use it to achieve message confidentiality. I will also discuss several classical symmetric encryption ciphers that use substitution operations. First, let's look at the basics of cryptography and what symmetric encryption is. The cryptographic systems are generally classified along three independent dimensions. 1. The type of operations used for transforming plain text to ciphertext. Now, all encryption algorithms are based on two general principles. One is substitution, in which each element in the plain text is mapped to another element. The element could be a bit, group of bits, letters, or characters. The other is transposition, in which elements in the plain text are rearranged or shuffled. So the data in the input is technically the same as data in the output, but just shuffled. And the fundamental requirement here is that no information is lost. In other words, the operations should be reversible. Most systems involve multiple stages of both transposition and substitution operations. They are referred to as product systems, and we will look at that later when we talk about block ciphers. Number 2 is the number of keys used. If both the sender and receiver use the same key for encryption and decryption, it is referred to as symmetric, single key, secret key, or conventional encryption. On the other hand, if the sender and receiver each use a different key for encryption and decryption, the system is referred to as asymmetric or public key encryption. Number 3, the way in which plain text is processed. A block cipher processes the input one block at a time, producing an output block for each input block. A stream cipher, on the other hand, processes the input continuously, typically 1 byte at a time, and produces an output byte for each input byte. So symmetric encryption is also referred to as conventional encryption or single key encryption or private key encryption. Both the sender and receiver here share a common key. This shared single key is used for both encryption and decryption. Since both sender and receiver are equivalent, either can encrypt or decrypt messages using this common key. Now, it was the only type of encryption in use prior to the development of public key encryption in the 1970s. And it remains by far the most widely used type of encryption today. All traditional schemes are symmetric with a single key used for both encryption and decryption. A symmetric encryption scheme has 5 elements, as shown in this figure here. Plain text, that is the original message or data that is fed into the algorithm as input. Encryption algorithm, which is the algorithm that performs various substitutions and transformations on the plain text. Secret key. This secret key is also input into the algorithm. The exact substitutions and transformations performed by the algorithm depend on the key. Ciphertext. This is the scrambled message produced as output. It depends on the plain text and the secret key. For a given message, 2 different keys will produce 2 different ciphertexts. Decryption algorithm. This is essentially the encryption algorithm run in reverse. And the idea is to get back the plain text. So it takes the ciphertext and the same secret key that was used during encryption to produce the original plain text. There are 2 requirements for secure use of symmetric encryption. 1, we need a strong encryption algorithm. At the minimum, we would like the algorithm to be such that an opponent who knows the algorithm and has access to one or more ciphertexts would be unable to decipher the ciphertext or figure out the key. 2. The sender and receiver must have obtained the secret key in a secure fashion and must keep the key secure. Because if someone can discover the key and knows the algorithm, all communication that is using this key is readable. It is important to note that the security of symmetric encryption depends on the secrecy of key and not on the secrecy of the algorithm. So it is assumed that it is impractical to decrypt a message on the basis of the ciphertext and knowledge of the encryption and decryption algorithm. So we do not need to keep the algorithm secret. Rather, we only need to keep the key secret. This feature of symmetric encryption is what makes it feasible for widespread use. Since algorithm need not be kept secret, manufacturers can and have developed low-cost chip implementations of encryption algorithms. These chips are widely available and incorporated into a number of products. Therefore, the primary security problem with symmetric encryption is maintaining the secrecy of the key. Let's look at the type of attacks on encrypted messages. This is known as cryptanalysis, which is the process of attempting to discover the plain text or the key. The strategy used by the cryptanalyst depends on the nature of the encryption scheme and the information available to the cryptanalyst. In ciphertext-only attack, all that is available to the attacker is the ciphertext. In general, we can assume that the opponent knows the algorithm used for encryption. However, in some cases, even the encryption algorithm is not known. Then with increasing information, we have 3 other attacks. In known plain text attack, the opponent must have some general idea of the type of plain text that is concealed in the message, such as English text, exe file, source code file, etc. A file that is encoded in a PostScript format, for example, always begins with the same pattern, which is %, exclamation mark, capital PS, hyphen, Adobe version. So many files or messages may have a standardized header and so on. These are all examples of known plaintext attack. With this additional knowledge, the analyst may be able to deduce the key on the basis of the way in which known plaintext is transformed. In a chosen plaintext attack, the analyst is able to gain access to the source system to insert into the system a message chosen by the analyst. So if the analyst is able to choose the messages to encrypt, then they may be deliberately able to pick patterns that can be expected to reveal the structure of the key. Then we also have chosen ciphertext attack, which is relatively less commonly used. Here, the analyst has access to the ciphertext messages. The analyst also knows the encryption algorithm that is being used. And the analyst is somehow able to select ciphertext and have the system somehow be tricked into giving the plain text for that ciphertext message. One can also use a brute force attack, which involves trying every possible key until an intelligible translation of the ciphertext into plain text is obtained. If the key space is very large, then this becomes impractical. On average, half of all possible keys must be tried to achieve success. Now this table here shows how much time is required to conduct a brute force attack for various common key sizes. 32 bits, which is supported by Blowfish Cipher, 56 bits, which is used in DES block cipher, 128-bit, which is used in AES block cipher, 168 bits, which is used in triple DES cipher, and then a 26-character key, which translates to 208 bits. You can see here that for a 128-bit key, the amount of time required to find out the right key at the rate of 10 raised to the power 6 decryptions per microsecond has drastically increased from 56-bit key. Therefore, today 128-bit key size is the minimum required key size for symmetric encryption ciphers. But of course, the larger the key size, the more secure the key is. Due to the impracticality of brute force attack, the opponents generally rely on the analysis of the ciphertext itself by applying various statistical tests to it. So only relatively weak algorithms fail to withstand a ciphertext-only attack, where the least amount of information is available to the opponent. Generally, an encryption algorithm is designed to withstand a known plaintext attack. Therefore, an encryption scheme is computationally secure if the ciphertext generated by the scheme meets one or both of the following criteria. One is that the cost of breaking the cipher exceeds the value of the encrypted information. Number two is the time required to break the cipher exceeds the useful lifetime of the information. Now we will examine a sample of some old symmetric encryption schemes. Although they are not used today, a study of these techniques will enable us to illustrate the basic approaches to symmetric encryption used today and the types of cryptanalytic attacks that must be anticipated. As I mentioned earlier, all encryption algorithms are based on two general principles. One is substitution and the other is transposition. In substitution ciphers, each element in the plaintext is mapped to or substituted with an other element. An element could be a bit, a group of bits, a letter, group of letters, or a symbol or a group of symbols. We will look at four classical substitution ciphers, namely Caesar cipher, Playfair cipher, Vigenère cipher, and one-time pad cipher, derived from the Vernam cipher. Caesar cipher is a monoalphabetic substitution cipher, whereas Playfair, Vigenère, and one-time pad ciphers are all polyalphabetic ciphers. All of these ciphers were used at some point in military communication or during wars. The Caesar cipher was used by Julius Caesar to send secret messages to his generals in the field. The Playfair cipher was used by British forces during World War I. Vigenère cipher was used in American Civil War. And one-time pad, which evolved from the Vernam cipher, was used to protect relay data in World War II. Let's look at the difference between monoalphabetic cipher and polyalphabetic cipher. In monoalphabetic substitution cipher, each element in the plaintext is always mapped to the same element in ciphertext each time it appears in the plaintext, as shown here in the example on the left. The letter L is always mapped to the letter M, no matter how many times it appears in the plaintext. In polyalphabetic substitution ciphers, each element in the plaintext is mapped to a different element in the ciphertext each time it appears in the plaintext, as shown here in the example on the right. The letter L is now mapped to N in one instance and to W in another instance. This makes the cipher secure by making letter frequency analysis harder. We will look at frequency analysis shortly. In Caesar cipher, you basically substitute each letter with another letter that is k positions forward. So the key basically tells you how many positions you need to move forward for encryption and how many positions you need to move backwards for decryption. So for decryption, you just move backwards to find the substitution. For encryption, you move forward to find the substitution. So to generalize, the encryption formula for Caesar cipher is P plus K mod 26. Here P is a plain text letter and K represents the shift, denoted by the key. Similarly, for decryption, we have the general formula C minus K mod 26. C is the ciphertext letter and K represents the shift. Now, when applying this formula, we have to work with numbers. So, in this table, you can see all letters of the English alphabet have been mapped to numbers. So, A maps to 0 and Z maps to 25. So, we have a mapping from 0 all the way to 25, as we have 26 letters in the alphabet. And we apply this modulo operation to ensure that the result of doing P plus K or C minus K always stays within this range of 0 to 25. So let's see how this encryption and decryption works in Caesar cipher. So let's say our plain text is the word hello and our key is 10, which means that every letter in the plain text will be substituted with another letter that is 10 positions forward for encryption, and then every letter in the ciphertext will be replaced with another letter that is 10 positions backwards to find out the plain text. So let's look at both encryption and decryption. Now for encryption, again, our formula is P plus K mod 26. So we have to find out the numerical mappings of every letter in the plain text and also of the key. Key is already a numerical value, which is 10. So looking back at this table, H maps to 7, E maps to 4, L maps to 11, and O maps to 14. So we will apply P plus K mod 26 on each of these letters. So for H, we will say 7 plus 10 mod 26, which is 17 mod 26, which gives you 17, and which is the letter R. Then for E, we have 4 plus 10 mod 26, which gives 14 mod 26, or 14, which gives you O, and so on. So the resultant ciphertext is ROVVY. Let's look at the decryption part. So for decryption, we have the formula C minus K mod 26. Again, from this ciphertext, we have to get the numerical mappings of all these letters. So R maps to 17, O maps to 14, P maps to 21, and Y maps to 24. So we will apply C minus K mod 26 on each of these letters. So for R, we have 17 minus 10 mod 26, which is 7 mod 26, or 7, which maps to the letter H. O is 14 for O we have 14 minus 10 mod 26, which is equal to 4 mod 26, or 4, which maps to letter E, and so on. So in this way, we get back our plain text, which is hello. So pause here and find out the answer to this question. Okay, assuming that you have solved this problem, you probably noticed that here when you applied the formula C minus K mod 26, C minus K resulted in a negative number. So how do you calculate the mod? An easy way of taking mod of a negative number is to just add the modulus to that negative number. So for example, for the letter B, we get 1 minus 25 mod 26, which is minus 24 mod 26. So we can just do this modulus calculation by adding 26 to minus 24, which gives us 2, which maps to the letter C. So Caesar cipher is the simplest cipher since there are only 25 possible keys, as each alphabet can only have 25 possible ciphertexts, and this is a monoalphabetic cipher. So by applying brute force attack, you can find out the key as the key space is so small, which means that given a ciphertext, you just have to try all 25 shifts of that letter backwards. So pause here and find out the plain text for this ciphertext by doing a brute force attack. Assuming that you completed this exercise, you probably noticed that the key is 2, so you didn't really have to try all possible keys. And the answer is easy to break. So how can we improve the security of monoalphabetic ciphers? Well, we can expand the key space. So instead of the 25 possible keys in Caesar cipher, where the shift was same for each letter, we could use a different shift for each letter in the plaintext. Here is one example of mappings of each plaintext letter in the English alphabet to a ciphertext letter. So here A maps to Q, which is a shift of 16. B maps to W, which is a shift of 21, and then C maps to E, which is a shift of 2. So instead of Caesar cipher, where we had a constant shift for all plaintext letters, now we have a different shift for each letter in the plaintext. So now we have a large key space, which translates to 26 factorial, since each set of alphabet mapping is a permutation of the 26 letters. We have a total of 26 factorial possible alphabet mapping sets. So the monoalphabetic substitution cipher is secure against brute force attack, but it does not sufficiently obscure the underlying language characteristics, since each letter in the plaintext is still mapped to the same ciphertext letter each time it appears in the plaintext. So how is this exploited? Human languages are redundant. As the example here shows, we don't actually need all the letters in order to understand written English text. Here you can see that the vowels have been removed, but you can still understand this sentence. Try to guess what this sentence is. Secondly, all letters are not equally used. In English, E is by far the most common letter, followed by T, R, N, I, O, A, and S. Other letters such as Z, J, K, Q, and X are fairly rare, so very few words actually use them. This graph shows English letter frequencies in the English text. Z is used least letter in English text, as you can see here, whereas E is the most used, as you can see here by this bar graph. So how can you utilize this information for analyzing ciphertext encrypted using monoalphabetic cipher? Well, you can do frequency analysis. If you have access to sufficient quantity of the ciphertext, you can plot frequencies of each letter in the ciphertext and compare it to English letter frequencies, assuming the plaintext was in English. For example, if we look at the graph on the right, which plots letter frequencies in ciphertext, we can see that S is the most frequent. Comparing it to the graph on the left, we can make a guess that the plaintext letter for S is probably E. Similarly, the ciphertext letter O could map to T, as it is the second most frequent in the ciphertext, and the second most frequent letter in the English text is T. This, along with some guesswork, can help the analyst discover the key. This technique can be applied to any language and, of course, not just English. Polyalphabetic ciphers try to make frequency analysis hard by reducing the spikiness of natural language text. As mentioned earlier, polyalphabetic ciphers use multiple cipher alphabets for each plain text letter. Therefore, the frequency distribution is sort of shuffled or flattened. So, for example, the most frequent letter E could be mapped to N as well as to G in the ciphertext. This will flatten the frequency bar of the ciphertext letters that E is mapped to, making it harder to guess the letter. We will look at 3 polyalphabetic ciphers, namely Playfair, Vigenère, and one-time pad. Playfair cipher was invented by Charles Wheatstone in 1854, but named after his friend Baron Playfair. It encrypts 2 letters at once, which means that it treats digrams in the plain text as single units and translates these units into ciphertext digrams. Here, digram is a pair of letters. The Playfair cipher uses a key matrix, which is a 5x5 matrix of letters constructed row by row using the secret key. The rules for filling this 5x5 matrix are that you first fill the key letters from left to right, after, of course, removing any duplicates. And then you fill the matrix with the remaining alphabet letters. So, for example, here the key is monarchy. So we have first filled the letters of the key from left to right here in the first row. And since we don't have any repetitions, we put all the letters of the key here in red. And then we have filled the remaining letters of the alphabet here. One thing to note is that wherever I appears in the matrix, you pair it with J and consider them as a single letter. This is because we just have 25 cells in this 5x5 matrix, but we have 26 letters in the English alphabet. Now, why I and J are paired is a choice made by the designer of this cipher, but you can also pair any other 2 letters together, but of course that has to be communicated between the 2 parties so that both of them can easily encrypt and decrypt the communication. Alright, pause here and complete this exercise, which is about making that 5x5 key matrix using the secret key Playfair. Since plaintext is encrypted 2 letters at a time, we first need to create pairs of letters or digrams. The pairs cannot have duplicate letters. Now, if a duplicate letter occurs in a diagram, we need to stop there and insert what is known as a filler letter between the duplicate letters and then create digrams again. Now, the filler letter is usually a least occurring letter, such as X. Now, this process is repeated until no diagrams have duplicate letters. Also, if the last diagram only has 1 letter, to make it a pair, we need to add the filler letter. So we will insert X with it. Let's say the plain text to be encrypted is the word balloon. And you can see over here we have duplicate letters. So the resulting diagrams are BA and then LL. But as soon as we look at LL, which has duplicates, we will pause here and insert a filler between them. After inserting the filler, we will create diagrams again. Now we have BA, LX, LO, and then ON. So now we have unique letters in all the diagrams. And also we don't have any diagram which just has one letter, so no need to add a filler at the end. Let's look at how to encrypt these diagrams using the key matrix we created earlier. There are 3 rules for doing that. First is that if both letters fall in the same row, each letter is replaced with the letter to the right. Of course, wrapping back to the start from the end, in case we have a letter at the very end. For example, in the plain text balloon, the letters in diagram ON appear on the same row, as you can see here in the yellow rectangle. So O will be replaced with the letter on its right, which is N, and N will be replaced with the letter on its right, which is A. So ciphertext is NA. Now, if both letters fall in the same column instead of in the same row, then we replace each letter with the letter below it. Again, wrapping to the top from the bottom in case the letter is at the very end. For example, again in the plain text balloon, the letters in the diagram BA appear to be in the same column as you can see here in the yellow rectangle. So B will be replaced with I or J, but they're the same letters. Let's just call it I. And then A will be replaced with B. So the ciphertext is IB. Lastly, if both letters are in a different row and a different column, each letter is replaced by the letter in the same row and in the column of the other letter of the pair. For example, in the plain text balloon, the letters in the diagram LX are in different rows and columns, as you can see here in this yellow rectangle. So L will encrypt to S, which is in the same row and in the column of the other letter in the pair. And X will be encrypted as U, which is a letter in the same row as X and in the column of the other letter in the pair, which is L. So our ciphertext will be SU. Similarly, the diagram LO will be encrypted to BM. The resulting ciphertext for balloon is therefore IB, SU, PM, and A. Now let's look at Playfair cipher decryption. So the decryption works exactly in reverse. First, we need to create diagrams from the ciphertext. Note that we do not apply the filler rule while creating diagrams on the ciphertext. We also need to create the key matrix. It is going to be exactly the same as that in encryption because we are using the exact same key for decryption. Then we apply the 3 rules on each diagram for decryption. Firstly, if both letters in the diagram fall in the same row, you replace each letter with the letter to the left, wrapping back to the start from the end. If both letters in the diagram fall in the same column, you replace each letter with the letter above it. And if this rule doesn't apply, then the last rule applies, which is that both letters in the diagram are in different row and different column, so each letter is replaced by a letter in the same row and in the column of the other letter of the pair. Lastly, you will remove any fillers that were added during encryption. Let's look at the decryption portion of the same example we did earlier. Here we are using the same key matrix since it is a symmetric encryption cipher, so the decryption key is the same as the encryption key. So we have 4 diagrams from this ciphertext. We have IB, SU, PM, and NA. Now letters in IB are in the same column. So to decrypt, we will look at the letter above each in the same column. So I will decrypt to B and B will decrypt to A. And if, for example, we were decrypting A, we will replace A with X. For SU, we will apply the third rule and take the letters in opposite corners of this yellow rectangle, which are L and X. Similarly, for PM diagram, the third rule applies, so the plain text is L and O. And for NA, the letters are in the same row, so we will take the letter to the left of each letter. So N will become O and A will become N. So our plain text is BALXLOON. And so we will remove X, assuming that this is the filler. Okay, so pause here and complete this exercise. Using the key table here, decrypt this ciphertext using Playfair Cipher. Okay, assuming you have completed the exercise, the answer is fireworks. The Playfair cipher is a great advance over simple monoalphabetic ciphers, since there are 26 into 26 equal to 676 digrams versus the 26 letters in monoalphabetic ciphers. So the identification of individual digrams is more difficult. Also, the relative frequencies of individual letters exhibit a much greater range than that of digrams, making frequency analysis much more difficult. The Playfair cipher was for a long time considered unbreakable. It was used by the British Army in World War I and still enjoyed considerable use by the US Army and other Allied forces during World War II. Despite this level of confidence in its security, the Playfair cipher is relatively easy to break because it still leaves much of the structure of the plain text language intact. So it can be broken given a few hundred letters. Another polyalphabetic cipher is the Vigenère cipher. This cipher encrypts letter one at a time instead of in pairs. However, first the key length is made equal to the message length by repeating the key letters. So in this example, the key is secret and the plain text is hello world. Note that the key has 6 letters and the plain text has 10 letters. So we will repeat the key letters to make the key length equal to 10. If, however, plain text is shorter than the key length, then we will discard the extra key letters. However, that scenario will be very unlikely. For Vigenère cipher encryption, we will make use of the Vigenère square, which consists of 26 rows. Each row is essentially English alphabet, circularly left shifted from 0 to 25. So the first row has a shift of 0, and the last row has a shift of 25, a left shift of 25. Each row and column also has alphabet labels. You can see here. To encrypt, we look at the intersection of row with the key letter label and column with the plain text letter label. So in this example, the key letter is S. So we will look at row labeled S, and the plain text letter is H. So we look in the column labeled H. At their intersection is the letter Z, which is our ciphertext letter. Now we will repeat this process for all letters in our plain text. For decryption, we will make use of the same Vigenère square. So now you will look in the row with key letter label. So our key letter here is S. So we will look in the row labeled S. Then we will keep looking in this row until we find the ciphertext letter, which is Z. So we find Z over here. So our plaintext letter is the label of the column in which Z is located. Therefore, plaintext letter is H. We will repeat this process for all the ciphertext letters. Okay, pause here and complete this exercise. Assuming you have completed the exercise, the answer is ZINCSPGVNU. The Vigenère cipher is pretty secure since there are multiple ciphertext letters for each plaintext letter. Hence, letter frequencies are obscured, however, not completely lost. The key to breaking Vigenère cipher is to identify the number of translation alphabets by finding out the keyword length that is repeated. So, a longer keyword can make breaking Vigenère cipher significantly hard. One-time pad cipher is a variant of the Vernam cipher, which was invented by Gilbert Vernam in 1918 to encrypt teletype messages. It uses a long tape of random letters, which are as long as the message, to encrypt the message using exclusive OR operation, or the XOR operation. Similarly, for decryption, the ciphertext is XORed with the same key letters. So again, the ciphertext is equal to plaintext XOR key, and plaintext is equal to ciphertext XOR key. So it produces random output that bears no statistical relationship to the plaintext, since each key is only used once. This figure explains the encryption and decryption process of one-time pad cipher. The message and key is converted in binary to show exclusive OR operation. The key is the same for encryption and decryption, because again, this is symmetric encryption. The table on the right here shows the XOR truth table and how the XOR operation works. So if both inputs are same, then the output is 0. Otherwise, the output is 1. So for encryption, you take each corresponding bit and XOR them together. So over here, during encryption, we have one bit as 0, the other bit is 1. So this translates to 1. Then we have 0 and 0, which translates to 0 because both bits are same. So you will keep repeating this for all the bits. And you do the same thing for decryption. So one-time pads are used in stream ciphers today. The one-time pad cipher offers complete security, but in practice has two fundamental difficulties. One is that there is the problem of making large quantities of random keys because every message is supposed to have a unique key. And then there is the problem of key distribution and protection, where for every message to be sent, a key of equal length is needed by both the sender and the receiver. Alright, so pause here and complete this exercise. Another example of a polyalphabetic cipher is the famous Enigma Machine. It uses a series of electromechanical rotor cipher machines and tries to incorporate the idea of one-time pad by using a different settings of these rotors each day. This machine was used by Germany during World War II. So watch the video at this link here to see how Enigma Machine works. You can also use the emulator